Okay, let's solve this LeetCode daily problem. We're given items. Items have prices and BUD values, and we're given queries. For each query, we have to find the maximum BUD of an item whose price is less than or equal to the value given in this current query. Let's say we're finding the answer for the third query at index 2. So we have given 3. It says find the maximum BUD of an item whose price is less than or equal to 3. So the first thing that we can do is to list all the items whose price is less than or equal to 3. So we have this item here, and this item is here, and we have 2, 4, and we have 3, 5. Among these 4 items, the maximum BUD is 5. So the answer for this query is 5. So that's why in the answers array, this is what we have to return. In the answers array, we have 5 standing at index 2 as an answer to the query at index 2. For example, let's do it for the query at index 1. It says find the maximum BUD of an item whose price is less than or equal to 2. So we have 2 items whose price is less than or equal to 2. So we have 1, 2, and we have 2, 4. Between these 2 items, the second one has the maximum BUD. So the answer to the second query is 4. Okay, this was pretty much the problem itself. And now let's move on to the explanation. Okay, this is the first approach that came to my mind. Since we're processing the queries, now every time when you see something related to processing queries, see if you can sort the queries in some way, in decreasing or increasing order, if the query and answering queries are independent. For example, in this case, the answering queries is independent. For example, you can start at anywhere, and since you're going to have an answer, so in your answers array, for example, let's say we are answering the query 4. So this asks us to find the maximum BUD of an item whose price is less than or equal to 4. So we would list all the items among whose price is less than 4 and less than or equal to 4, and then find the one with the maximum BUD. So the prices are independent. For some reason, you can sort the arrays. So in this case, actually queries is sorted. This is the first input. But if it is not sorted, sort the queries, because in a sorted order, processing queries is much more easier. Now I'll show you why. Now let's say we answer the query 1. This requires us to find all the items whose price is less than or equal to 1. There's only one. This one here, right? And for this reason, the answer for the query 1 is 2. Now we're answering the query for 2. So that means, okay, let's find all the items whose price is less than or equal to 2. Okay, finding all the items whose price is less than or equal to 2 requires us to find all the items whose price is less than or equal to 1. But we've already done that. So because we have processed this query before. So that's why the sorting in increasing order and processing it this way is easier, because now we don't need to go back and list this item again, and we don't need to iterate from the beginning. We can just start here. So we can just start here. Now in fact there is a problem now, because we have to sort the items as well. So let's, for this reason, sort the items as well. Okay, now we have sorted the items array. This is the original one, and this is the sorted one. Now we need to redo the process again. So let's just start from the first query, and now let's say we're answering the query 1. We list all the items whose price is less than or equal to 1. We start at the first index. We have this item whose BUD is 2. So we keep track of this. and we don't have any other item whose price is less than or equal to 1. So for this one, the maximum beauty is 2. Now we move on to to the next one, to the next query. So this is going to be, so the answer is going to be 2 for this one, right? So then we move on to this one, the query 2. 2, we find all the items whose price is less than or equal to 2. We have only one item again, and we keep track of the maximum. We have the maximum from the previous one was 2. Okay, let's write this like that. Okay, the maximum was 2 when we process the query for the items whose price is less than or equal to 1. We already have this 1, 2 here, whose beauty is 2, and now we have 4. We update our maximum, so we have 4. So the answer to this query is 4. Now we move on to the next query. This is 3 here. So we move this to here and update the max. Max does not, okay, the max does not get changed. And then we move to the next query, to the next item. So now we have 5. The max updates to 5. And that's all. That we don't have any more items whose price is less than or equal to 3. So now we put 5 at this spot here. Now we move to 4. We include all the items. So 5, we want to start here, but 5 is greater than 4. So we don't do anything. So we put 5 for this one again. The max still stays 5. So for 5, now we're processing this one. Now we can include this query, this item here, and the max gets updated. Max becomes 6. So we have 6 for this one and 6 for this one. So this was the first idea that came to my mind. So what I did is to sort the queries. In fact, in the first example, the queries were sorted, but if it was not, then we sorted in increasing order. And because sorting it helps us, but when you know all the items and the maximum beauty of the items whose price is less than or equal to 3, you can find the maximum beauty of the items whose price is less than or equal to 4. Because you don't need to iterate among the items whose price is less than or equal to 3, because you already have the answer for this one. You already know that, okay, from the previous query, the maximum was 4. Now you just need to go and find the items whose price is less than or equal to 4 and update the maximum if appropriate. And otherwise, we don't do that. So processing in this order, in increasing order the queries, helps us to find the maximum beauty quickly. So this takes us since we sort the 2 arrays, it takes n log n. Okay, we have some factor, but we end up with an n log n algorithm. So we do actually two pointer sort of stuff. This is a linear, but this gets suppressed by this time complexity. So the time complexity of this one is n log n while we sort twice. We sort the items and we also sort the queries. So this was the first approach, and I'll show you another approach where we only sort the items but not the queries. And then we use binary search, which we end up with another n log n algorithm. Okay, this is the code for the first approach. We have queries. So I keep track of the query itself and its index because I'm going to sort the query. So in this case, the indices will change its place, but we don't want that because then we wouldn't know where to put that in the answers array. And then we have the sort queries, and we sort the queries and we sort the items, and then we have the answer, and we will on the go, we will keep track of the maximum value, and this is j. This starts at the first index of items, so index 0, and then we say, okay, let's process the query 0, and then we say while we have items and the current query's value is greater than the item's price, greater than or equal to item price, okay, then update the maximum and move to the next item. As long as this is true, we will keep tracking of the maximum. And at the end, so we use the original index of the query, not this index here, I. So we have answer queries indexed as second, and we put the maximum there. That way we keep track of the maximum, and the time complexity is mainly because of this. It's O of n log n. Now I'll show you the second approach. Now let's discuss approach 2. In approach 2, we don't sort the queries array. We do something different. Now we have sorted the items array, but instead of sorting the queries and then finding and keeping track of the maximum, for a query, let's say 3, right? We'll find the last value, the last item whose price is less than or equal to 3. This is this item. So from here to here, all items have prices less than or equal to 3. So this is the last one, right? Now we need to know the maximum beauty. Now how do we know that? Do we have to go back to the first index and iterate to this index and find the maximum? But instead of doing that, we can do a little bit of pre-computing, and then we can get the maximum for every index in O1. So that was the solution for this part of the problem. So for this reason, what we do, we create a max array for the given items. Now, how many items we have? We have 5 items, right? 1, 2, 3, 4. And index 0, index 1, 2, 3, and 4. For index 0, the max is 2. For index 1, the max is the maximum of the previous index up to here, which is 2, and they updated with the current maximum of this item, which is 4. And the max for this index, this item here, up to this index is going to be 4 again. And now we update it to 5. Now for here would be 6. Now what this max array says us, it says that, okay, if you ask me what is the maximum beauty of items from 0 to this index, it's 4. If you ask about the maximum beauty of the items up to this index 3, it is 5. So that's how we get this answer in O1. And the other one, now how do we find the last item? So let's keep it here. We said for request 3, now how do we find the last item, which was this guy here, which is less than or equal, has a price which is less than or equal to 3. So we have to find this one, right? So for this reason, we use binary search, since the items are sorted in increasing order of their prices. We can use the upper bound to find. So if, for example, if we use upper bound on this index, it will find this one. It says, okay, this item has a price greater than 3. So then the previous item must have a price less than or equal to 3. And I want to warn you that it's possible that you have a price. Let's say if there was 0, if they were asking about items with prices less than or equal to 0, then we don't have such an item. So in this case, the answer would be 0 to this query. Or let's say among all the items, the smallest price is 5 and they're asking a price of 3 in the queries, then there is no item with price less than or equal to 3. So in this case, the answer would be 0 for this problem. We use the upper bound to find this one, and we just subtract 1. This will lead us to the item with the last item, which has price less than or equal to the current query value, which is 3 in this case. So we use the upper bound. So let's recap what we did. We sort the items based on their prices, and we didn't do anything on the queries. We'll just process them in the given initial original order. And we created a max array. This max array tells us the maximum beauty up to the given index, including the given index. The maximum beauty of the items up to this given index. For example, for 3, the third item, the fourth item, actually it's going to be 5. This is 2, 4, 2, and 5. So 5 is the maximum beauty. So that tells us the maximum beauty in O1. And then we use the binary search. This is add a log factor here to find the last item, which has a price less than or equal to 3, and then we use the max array to find the maximum beauty. So we only sorted the first array, that is n log n, but we're still processing all the queries, and for each query we do a binary search, that's another n log n. So it's almost the same as the previous approach, but in a little bit of different manner. So we actually have used an auxiliary space as well. This is an O(n) for the items length. So this is n here, the length of the items array. This is the code for the second approach. We have n queries and m items. And again, the max beauty here is the maximum beauty of items up to the given index. So given index for the up to the given index of the items. And then we only sort items. And then we store the maximum for each item, for each index. That's the pre-computation for the max beauty array. And then we create the answer. We use the upper bound, which is the binary search. In this case, we use the upper bound to find the upper bound finds for a given value, finds a value in the array that is greater than it. So in this case, the item will point to that value. So from item, it's an iterator. So we subtract the beginning of the array. It gives us the index of that array. But this index, as we said, is pointing at an item value that is greater than the current value here. So if we go back one element, the one index, then it will be a value that is less than or equal to the given queries. But it is possible that if this is -1, then that means there is no item with price less than or equal to the current value. So in this case, we'll just skip it. Otherwise, we'll put the max beauty at the given index into our answer.